Now let's rewind and go back to the beginning. This time, we really mean the beginning. If we mentally reverse the expansion of the universe, we get to a point where everything was in the same place at the same time. Knowing how far the galaxies are from one another now, and knowing how fast they continue to move away from each other, it's possible to calculate a moment in time when they were all together at the same place. That moment was 13.799 plus or minus 0.021 billion with a B years ago, according to the latest data. This moment, that long ago, was the moment of the Big Bang. Now, what is the Big Bang? It's a concept we've heard quite a bit about and a phrase that's constantly mentioned in physics and astronomy and even common conversation sometimes. But let's take a moment to really break it down. According to dictionary.com, the Big Bang is a theory that deduces a cataclysmic birth of the universe from the observed expansion of the universe, cosmic background radiation, abundance of the elements, and the laws of physics. Great. Easily understandable and no further explanation needed. Actually, I'm totally kidding. We definitely might want a second or third opinion, so we go to NASA's Space Place to see how the Big Bang is defined there. Here it's described as the idea that the universe began as just a single point, then expanded and stretched to grow as large as it is right now, and it's still stretching. But the most concise yet thorough explanation yet is that of NASA's Goddard Space Flight Center, which states that the Big Bang model is a broadly accepted theory for the origin and evolution of our universe. It postulates, meaning that it theorizes, that 12 to 14 billion years ago, the portion of the universe that we can see today was only a few millimeters across. It has since expanded from this hot, dense state into the vast and much cooler cosmos that we currently inhabit. We can see the remnants of this hot, dense matter as the now very cold cosmic microwave background radiation, which still pervades the universe and is visible to microwave detectors as a somewhat uniform glow across the entire sky. We'll learn more about the cosmic microwave background radiation later in this unit, but for now we can say that in a nutshell, the Big Bang is the theory that describes how all of space, matter, and energy formed from a dense primordial atom of energy. And no, it was not an explosion either, despite how it's often depicted and discussed in everyday media as such. So, who came up with the Big Bang? Surely someone had to have suggested the idea before it snowballed into what it is today. And that person was Georges Lemaitre, who was also known as the father of the Big Bang. Coincidentally, this is a perfect description for the Belgian physicist and Catholic priest who is credited with having said, "I have seen Genesis." Here he is pictured with Robert Andrews Millikan, the first president of Caltech, and another physicist whose name we may already know. This photograph was actually taken at Caltech in 1933, just after Lemaitre had finished presenting a lecture of his work. Interestingly enough, some of this work included a publication of something very similar to what Hubble had published in his development of what's now called the Hubble Law. But Lemaitre published his findings 2 years earlier, which is why the Hubble Law is sometimes called the Hubble-Lemaitre Law, since both came upon the same concept independently of one another. Now, let's go ahead and understand the timeline of the Big Bang. What happened in the moments immediately following this burst? In fact, these first few moments are crucial in our understanding of how the universe continued to develop, and we must take a closer look at the first 3 minutes of that timeline to understand these concepts better. These first 3 minutes are so significant that there are entire books and publications about what was speculated to have happened in that time period. The main thing to consider during this time is what's called Big Bang nucleosynthesis. We always talk about hydrogen and helium being one of the first elements to exist in the universe, but when exactly do they come in? To answer this question, we have to look back at the first 3 minutes, and here we encounter Big Bang nucleosynthesis. Now, initially, conditions were too hot for protons and neutrons to exist or survive. Instead, all matter existed in the form of a quote-unquote quark soup. A quick side note, A quark is a subatomic particle which, when combined with other quarks of different types or flavors, can form protons and neutrons. Inside the atom's nucleus are protons and neutrons, but inside the protons and neutrons themselves are quarks. A proton is made of 2 up quarks and 1 down quark, and neutrons are composed of the opposite, 2 down quarks and 1 up quark. The colors are arbitrary here, even though there must be at least 1 red, 1 blue, and 1 green. In particle physics, these colors do carry some significance, but for now, we don't need to worry about it. Electrons, however, are in an entirely different category of particle and are not composed of any subatomic particles because they are elementary particles themselves. Understanding these concepts more thoroughly would require a deeper dive into particle physics, which you can do on your own time if you're interested in that, but we won't be focusing on these details for this class, even though there are a lot of cool things that we could discuss there. But anyway, this is good enough for now. During the first 4 seconds of the universe, particles formed by pair production, where these subatomic particles combined to form pairs of particles like protons and antiprotons, which are actually different from neutrons. Then after 2 minutes, deuterium formed by the fusion of protons with nearby neutrons, and after 3 minutes, helium formed by the fusion of the newly formed deuterium with other protons and neutrons floating nearby. Now, if we were to map this time period on the cosmological timeline, tracing all the way back from today to that moment, we would have to go back almost 13.8 billion years to see it on the full scale. All of what was just discussed in the first 3 minutes took place in this portion of the timeline. And it's also worth noting that the time intervals here are not regularly spaced either, despite the fact that these similar-looking intervals actually end up representing larger and larger gaps in time if you pay attention to the labels. To get a full sense of the scale of this image, we can look at this small point of bright light in today's universe, and we'll see that this point is actually a region of the universe where clusters of galaxies and solar systems are clumped together. Another view of the expansion of the universe since the Big Bang is this 3-dimensional bell-shaped diagram, put together using observational data from the WMAP mission, which we'll hear more about in just a few minutes. Pause the video now if you'd like to take a closer look at this image, or you can also let it keep playing as we move along into the next topic. Here we see a branch diagram demonstrating the development of the 4 fundamental forces of the universe over time. These are the strong force, the electromagnetic force, the weak force, and gravity. All 4 forces are believed to have initially been unified as one force at the very beginning of the universe. Gravity is the first of the 4 to branch off and become its own distinct force, separate from what will eventually continue to split into the remaining 3 forces. This occurs merely a fraction of a fraction of a fraction of a millisecond after the Big Bang. To be more specific, 10 to the power of negative 43 seconds is even smaller than a trillionth of a trillionth of a trillionth of a second. The fact that the remaining 3 forces separated later in time is the fundamental idea of the grand unified theory, which states that earlier in the universal timeline, when the temperatures were much higher, hotter than even the cores of stars, these 3 forces were still indifferentiable from one another. When the temperature of the universe cooled down to 10 to the power of 27 Kelvin, which took practically no time to happen, the strong force, responsible for holding subatomic particles together, became the second force to separate off into its own distinct branch, leaving behind the electroweak force, which shortly thereafter separated into the electromagnetic force and the weak force, creating a total of the 4 fundamental forces that still exist to this day. As we go further back in time, closer to the Big Bang, the higher the temperatures of the universe, and therefore of the particles that came into existence at these times. Tracing our way back to the very root of the 4 force branches, where they are all still combined as one force, indistinguishable from one another, is described as the all-encompassing theory of everything. Now, this is all good and great, but where is the evidence? Mere seconds after the Big Bang, the universe was really hot, with a temperature over 10 to the power of 32 Kelvin. That's 100,000 billion Kelvin. That much heat implies a lot of energy, which means that there must be some extremely short wavelength electromagnetic radiation that's associated with the Big Bang that could be detected. There must be evidence of this, and it was detected. Accidentally. We'll find out more about this accidental evidence in the next video.